Section 1.6, Solving Linear Inequalities. So the first part of the section talks about simple inequalities. Again, throughout the section there are highlighted terms. Those are vocabulary terms that you do need to know the meaning of. They will be used in class. They will be used in directions to homework, quizzes, and tests. So we're going to look at an example of a simple inequality, a true simple inequality. 3 is less than 5. And we're going to go through some basic transformations on that inequality, adding the same quantity to both sides, subtracting the same quantity from both sides, multiplying both sides by the same value, and dividing both sides by the same value. In the left-hand column, the value that we're adding, subtracting, multiplying, or dividing by will be a positive value, in this case positive 2. And on the right-hand side, that value will be a negative value, negative 2. So what you see in the first part of this slide here is I've taken 3 is less than 5, I've added positive 2 to both sides of that inequality, and I have another true simple inequality, 5 is less than 7. Here in the right hand column, again, I've taken that same inequality, added negative 2 to both sides, and I still have a true simple inequality, 1 is less than 3. Now, same concept, but now I'm subtracting, so I subtract positive 2 from both sides from that original inequality, and I still have a true simple inequality, 1 is less than 3. If I subtract negative 2 from both sides of that simple inequality, I still have a true simple inequality, 5 is less than 7. Now here, if I multiply both sides of the inequality 3 is less than 5 by positive 2, I have a true simple inequality, 6 is less than 10. If I multiply both sides of that simple inequality by negative 2, I get a false simple inequality. Negative 6 is not less than negative 10. Negative 6 is actually greater than negative 10. Finally here, I'm dividing both sides of that simple inequality by 2. I get a true simple inequality. 1.5 is less than 2.5. But here in the right-hand column, if I divide by negative 2, I get a false inequality. Negative 1.5 is not less than negative 2.5. Negative 1.5 is actually greater than negative 2.5. And this is meant to demonstrate the difference between solving linear inequations and solving inequalities, simple inequalities. When I multiply or divide both sides of an inequality by a negative value, in order to maintain a true statement, I have to actually flip the inequality symbol. So you can see here when I multiplied by negative 2, in order to maintain a true statement, a true inequality, I flipped the less than sign to greater than. When I divided by negative 2 here, I had to flip this less than sign to greater than. So earlier we looked at transformations that produce equivalent equations. For inequalities it's similar except for the case we just looked at. When you multiply or divide both sides of an inequality by a negative number, you have to reverse the inequality symbol. That's the difference between solving equations and solving inequalities. Multiplying or dividing by a negative number means reversing the inequality symbol to maintain the truth of the statement. The graph of an inequality in one variable consists of all points on a real number line that correspond to solutions of the inequality. To graph an inequality in one variable, use an open dot if the inequality symbol is less than or greater than. Use a solid dot if the inequality symbol is less than or equal to or greater than or equal to. For example, a graph of x is less than 3 would mean an open circle at 3, because 3 is not less than 3, but then everything to the left of 3 would be true. So all those values are indicated. To graph x is greater than or equal to negative 2, I would put a solid dot at negative 2, and then all those values to the right, or greater than negative 2, would be indicated. Oftentimes when I draw these graphs, I'll indicate values to the left or to the right instead of shading the line, I'll actually just go up and above the line like this to indicate. So this is my typical way of showing x is less than 3. Again, open circle at 3. Solving an inequality. So in this inequality, 11y minus 9 is greater than 13. I add 9 to both sides. I divide both sides by positive 11, dividing by a positive value. The inequality symbol stays the same, so greater than throughout this solution. Final answer, y is greater than 2. In this example, solving the inequality, I subtracted 10x from both sides to get negative 3x on the left-hand side of the inequality. I subtracted 9 from both sides to get negative 21 on the right-hand side of the inequality. And now I divide both sides by negative 3. So negative 3x divided by negative 3 is 1x. Negative 21 divided by negative 3 is 7. But because I divided by a negative, I flipped the inequality symbol. Greater than or equal to becomes less than or equal to. So pause this presentation and try number 26 on page 45. 7 minus n is less than or equal to 19. So I subtracted 7 from both sides to get to this second line. And then I multiplied both sides by negative 1. The opposite of n times negative 1 is n. 12 times negative 1 is negative 12. Because I multiplied both sides by a negative, I flipped the inequality. Less than or equal to became greater than or equal to. And then graphically, n is greater than or equal to negative 12, means a solid dot at negative 12, and then everything to the right of negative 12, every value that's greater than negative 12. The second part of section 1.6, solving compound inequalities. See at the top of the slide, a compound inequality is two simple inequalities joined by the conjunction and, or joined by the conjunction or. So there are two examples. On the left-hand side is an and compound inequality. The way that would be read is that x is greater than or equal to negative 2 and less than 1. So the values for x that satisfy that inequality are all those values that are both greater than or equal to negative 2 and less than 1. The values in the solution set have to satisfy both conditions. These highlighted values satisfy both conditions. So all these values that are indicated here are both greater than or equal to negative 2 and less than 1. In the right-hand column, this is an or compound inequality. X is less than negative 1 or x is greater than or equal to 2. For a value to be part of the solution set, that value only has to satisfy one of those two simple inequalities. If the value is less than negative 1, or if the value is greater than or equal to 2, then that value is part of the solution set. Graphically, I indicate that as two separate pieces. X is less than negative 1 is indicated here on the left-hand side of the number line. X is greater than or equal to 2 is indicated here on the right end of the number line. So in this case, with an or compound inequality, values in the solution set only have to satisfy one of the conditions. To solve a compound inequality, it's very similar to a simple inequality. It's just that there are, in this case, for an and compound inequality, 3 sides. So in this case, I subtract 4 from all 3 sides. Negative 9 minus 4 is negative 13. T plus 4 minus 4 is t. 10 minus 4 is 6. And algebraically, the solution is t is greater than negative 13 and less than 6. For a compound inequality where it's an or inequality, I simply take the two simple inequalities, solve them separately. So solve this inequality, this simple inequality separately and get x is less than negative 1. Solve this simple inequality and get x is greater than 7. And then I can indicate those graphically here or algebraically here.